So I'm Kuntai, and I'm a PhD student from U Chicago, and I'm working in vLLM for this summer, and now I'm back to finish my thesis. And my work is mainly on disaggregated prefill and performance benchmark, and also recently I'll be working on KV cache sharing, and yeah. So yeah, to, as for the outline, I'm planning to talk about the distributed inference and initial PR on disaggregated prefill, and also I want to talk about some KV cache sharing across vLLM, including faster KV cache delivery and composing multiple KV caches. So let's start. Okay, let's start from the first one. Okay, so basically, I guess not like after talking to a lot of industry people, I feel like not all people know why we need to do like prefill decode disaggregation. So I'm planning to do a brief introduction on why we need to do that. So basically, the intuition is that if we put prefill and decode functionality inside the same node, there will be some contentions. And more concretely, the inter-token latency will be high when we batch the prefill job together with the decode job because prefill is slow. And also, if we put the prefill and decode in the same node, they will share the same parallelism strategy so that you cannot change only the time to first token, which is dominated by prefill, or only the inter-token latency, which is dominated by decode. Like if you change the parallelism strategy, it's always changed simultaneously so that the inter-token latency and time to first token is changed simultaneously. Yeah. And beyond the contention in terms of putting the same functionality together in the same node is also appears in other scenarios. An example is speculative decoding. So we observe that when the workload is low, there will be available GPU cycles for the LLM system to run the speculator and gives us bonus throughput. But when the workload is high, if we spend GPU cycles on the speculator, it actually slows down the inference. So yeah, so basically because of the contention between LLM and the speculator, we cannot enjoy the extra throughput by the speculative decoding and the high workload. Yeah, that's a second case. And also we also have a third case, which is multimodality. So in multimodality, the image encoder is typically computation bounded, which means that its arithmetic intensity is high, but large language model, in contrast, is memory bounded. So ideally, we want to put them on different devices for the best performance because they are bounded by different resources and different hardwares has different resource bound and has different computation memory trade-off. So as a quick summary, like we can see that probably like the inference will will change from co-locating on the same node to a more distributed view where each node is only do one single job. It can be prefill, it can be decode, it can be speculative decoding, or it can be the imagery encoder. And they are communicating through a communication instead.
One,
And sorry, is there a question in the audience? Okay, I'll continue. Yeah. So basically, we can put computation-bounded modules on hardwares with higher computation per dollar, and we can put memory bandwidth-bounded modules on GPUs with higher memory bandwidth per dollar. Yeah, and that gives us a better performance overall. So, of course, the key is to build the middle part, which is the tensor transmission part. So, but we need to understand what tensor is being transmitted in this module first. So basically, here we are transmitting the different modules here is transmitting the different LLM request states. And large language model request states is mainly tokens and KV cache. It's just tokens and KV cache, not other things. And we focus on KV cache because tokens is really small. KV caches is like, yeah, should be like tens of thousands of larger than the tokens itself. Okay, so to build this tensor transmission library inside the LM, I submitted initial PR, and the reason of like basically there is a lot of preceding effort on this to do the prefill decode disaggregation and putting communication between them, but they somehow all end up like closed or become closed PRs or become not actively working. So the main reason is that they're trying to implement the prefill decode worker inside the same vLLM engine, and that requires almost two set of copies of everything. By everything, I mean two set of memory allocator two set of KV cache engine and two set of scheduler. And we all know that the memory allocator, KV cache engine, scheduler is already hugely complicated. And if you want to further modify its logic and further perform synchronization between two sets of these modules, is even more trickier. So those PRs typically incurs like thousands of line of code change only on the merely in the core module, and also a lot of surrounding changes to do testing, and also introducing new libraries to do communication. And compared to that, I'm taking another way of implementing this disaggregated prefill functionality, where I will create prefill vLLM instance and decode vLLM instance. I'll put them into separate instances instead of putting them together inside one vLLM instance. And then I will build connections between instances using Echo. And the result is that I only need to implement about hundreds line of code on vLLM core, of course, excluding the distributed communication part. And the performance is not bad, actually. So the end-to-end latency of transmitting about 2,000 tokens on Llama 8B is about 60 milliseconds. And it can be further optimized, and we will further optimize that. Yeah. And this will conclude the disaggregated prefill part. Is there any questions here? Oh, I saw some chats. Let me see.
Yeah, I think the chat was just unrelated.
I see. Okay.
Actually, I did have one quick question, so you can jump in. When you said you're transmitting using nickel, what specifically, which collective are you using for that?
Only send and receive.
So it's peer-to-peer.
Yeah, P2P.
Got it. Okay. That's what's curious. Thanks.
Yeah. So basically, in this, like different from like tensor parallelism, it's more like pipeline parallelism where you only need to do send and receive.
Got it. Okay. Thanks.
Okay. So I'll continue, but feel free to interrupt me in the middle. Yeah. And the second part will be KV cache sharing across vLLM, including faster KV cache delivery.
I have another question related
Sure.
to the previous. So my question is what if one of the instance is quite available at some moment? Like if the user is sending like extremely long prompt, then maybe the decode part will be quite available. Is that the case? Will be considered?
Yes. Yeah. So to answer that question, so basically just to echo what the question, so you are saying that if the user is sending a very long input where it kind of like is prefill dominant, then the decode node will just sit there and do nothing for a long time. Is that right?
Yes.
Okay. Yeah. So basically the best scenario for disaggregated prefill is that the prefill decode ratio is relatively fixed, so that you know, like you roughly know it beforehand. For example, maybe who knows, maybe I'm a random company and I know that my input tokens is about 4,000 and my output token is about 100 or even more. And then the prefill decode, the workload of prefill decode is relatively fixed, so that you can just allocate fixed amount of prefill node and fixed amount of decode node. But in the case where the prefill suddenly becomes dominant, yeah, it will result in inefficiency, like the decode node needs to wait.
Okay, so there's no like a automatic mechanism to, just switch a decode instance into a prefill instance.
This is a more deployment related question. So
okay. So we need to decide before. Oh, I see.
Yeah, so basically the current industry practice is that they will have some flexible node. By flexible, I mean that they can do prefill or do decode. And if the workload is fluctuating, you will use the flexible nodes to help you handle the workload.
I see. So another related question is when we say instance, which means it will be assigned with a single card or a process or a node, or what is a
here, the instance, what I mean by instance is a single model replica.
Model replica, which is running in a specific process or a thread?
It can be run on one GPU or multiple GPUs, or even cross node, but it's one single model replica.
Okay, got it. Thank you.
Yeah, thanks for the question.
I have another question. So if you're using Nickel, does that mean that currently it only works for NVIDIA?
Yes.
Okay.
Sadly, that's the case. Yeah, but
Yeah.
we want to first make sure we support the NVIDIA case and then expand to other cases. And so basically, in my experience, the infrastructure support for NVIDIA is slightly better. And so I actually tried to use the AMD series of communication, and I'm facing some troubles. So we will support that in the future, but not for now.
And is there a performance comparison with disaggregate prefill versus a chunk prefill?
Yes, and it's so basically yes, and it performs better, but under very certain workload. So basically, because I'm mainly testing it in one node, and I'm doing like 1 versus 1 allocation. By 1 versus 1, I mean 4 GPUs for decode and 4 GPUs for prefill. In that case, the workloads prefill and decode runtime needs to be roughly balanced, which is roughly translated to like 2,000 tokens and just 10 output tokens. In that kind of really idealized workload is better. But in order to get real practical benefit, we need to allocate multiple prefill node, one prefill node and multiple decode node, because the decode is typically the dominant part. So for that setup, I haven't tested yet because I need the test bed, and I sadly don't have one for now.
I see. And speaking to the best scenario, how much improvement we can get? 10% or?
What's your improvement metric? So there can be two types of improvement metric.
I think when we say better, I assume it's throughput. Maybe I'm wrong.
Just want to clarify, disaggregated prefill does not increase throughput.
Oh, okay.
Yeah, disaggregated prefill mainly improves the percentage of requests that meets the SLO.
Oh, I see.
And it
So
also
for
can improve things like time to first token, right?
Yes.
Yeah. Because
Oh,
whereas
okay.
Yes.
prefill would take more time to process a prefill coming in, whereas with disaggregated prefill, you can just immediately, process that.
So basically, the practice is that they will assign different parallelism strategy in between prefill and decode, which is not doable in chunk prefill.
I see.
Yeah, they will hugely parallelize the prefill to make it much faster. Yeah.
And it also depends on it also depends on the length of the prompt. If I'm sending, I assume if there's some case that some of users are sending like very short prompts, like under 100 tokens, and the others are sending like 4K, then they will be just distributed to different batch, right? Or they will be in the same batch. I assume should be not.
That's a more concrete question. So I will say that depending on the scheduler part. Yeah.
Kuntai, I love the questions. This is amazing. This is one of the first time actually having live questions like this, but let's move on for a second just to make sure we get through most of the stuff and then we can come back to questions.
Okay. Yeah. Sorry, I will
Thanks so
continue.
much.
Yeah,
No,
thanks
no,
for the
no, no.
reminder. Yeah. Okay. So let's do the second part will be the KV cache sharing across vLLM. So basically here the vLLM, in vLLM's worldview, each vLLM instance is just one single instance that handles everything inside it. But there needs to be more infrastructure support to handle the things between vLLM instances, and that's why I'm here to do the KV cache sharing. So as a quick pitch, basically it's because large language models are more powerful when paired with a very long context called knowledge. Let's call it knowledge. And so here the LLM, the user will send a short query, but we need a very long context to make sure we correctly answer that query. And the long context can be of different format, like book, news, business docs, or chat shopping history. For example, maybe today I'm wondering what's the news today, and that requires a long document for the LLM to answer that question well. Yeah, so LLMs needs to read a large amount of data in order to correctly answer my question. And but if the document is really long, it takes a lot of time to prefill. Yeah, here's a really slow animation of prefill to show it's slow. Yeah. Okay, so the prefilling can take the majority of the time when handling with long context. And what we want to do here is that we want to share KV cache across vLLM to make the prefill much faster. Yeah, and our goal here is that you only prefill once on each different type of text, so that you don't need to repeatedly prefill them on different vLLM instances or across different runs on the same vLLM instance. So what we want to do is to share the KV cache, which we call as knowledge. And the concrete benefit is that it will have faster, shorter TTFT and higher throughput because it does not need to rerun the prefill computation. And also, most of the time, the knowledge will be reused because of 2080 rules. And it won't be too expensive. It will actually be cheaper if you store the KV cache on disk compared to redo the computation, even if the hit rate is low. So we did a rough calculation. If your hit rate, the cache hit rate is above once per hour, it's economical to store it on the disk. And what we envision is that this kind of like knowledge sharing system will have 3 components. And the challenge is like there will be several challenges. So basically, one of the challenge is the KV cache is large, so we need to load it real fast. And there's one key technique for us to do that. And the second challenge is that if the text is no longer a prefix, then the KV cache cannot be directly reused. We need to do some tricks there to make sure we blend the KV cache together so that it can still be reused. And there's another key technique we're using here. And let's dive into the first key technique first. So yeah, this will be our recent publication where we do KV cache compression for a faster KV cache loading. And yeah. So here, the left-hand side is the standard vLLM engine, and right-hand side will be LM cache plus vLLM engine, so that it can kind of like steal the KV cache from the standard vLLM engine to accelerate its inference. And the context is a FFmpeg documentation, which FFmpeg is a kind of like a software. And here, let's type an example queries here. So for example, maybe tell me what is FFmpeg in 10 words. Yeah. Hopefully it works. Yeah, it works. And the response delay is about 2.34 seconds. And here the response delay is 0.16 seconds. So it's like from 2.34 to 0.16. It's like about 20x faster. Yeah. So here we are using this technique to compress a KV cache for faster prefill. So the issue is that even if the KV cache can help us skip the prefill, we need to load it first into GPU, and the loading can take forever. So what we want to do here is that we compress the KV cache, which can significantly decrease our loading time, and then load it back to GPU and do inference. So this will give us faster prefill, even if the reused KV cache is loaded from a remote disk, and it can still give us speed up. And here's a very rough view of our technique. So the KV cache will go through the encoding to a binary representation, and we store it in the disk storage. And then upon request, we will retrieve the binary representation and do GPU decoding to make it decompress KV cache and load it back to the vLLM for inference use. And yeah, and after talking to industry, like a lot of guys about this, their main impression to KV cache is that it's just random tensor. You cannot compress it easily, but it's not. So the KV cache is not random, and it can be compressed because the KV cache is similar between neighboring tokens. The tokens itself can be hugely different, but the KV cache is similar. And we found a part of a KV cache are less sensitive than others for quantization. And also, the quantized KV cache can be entropy encoded with fewer bits. So let's dive into the first property. KV cache is similar between neighboring tokens. So here's a figure. Basically, we're trying to extract one layer of the KV cache here, just a layer, and we plot it on the right side. The x-axis is the token, the y-axis is the channel. And you can see that the horizontal artifacts there, which means that the KV cache is continuous, like along token dimension. So the opportunity is that the KV values are at nearby tokens are very similar, and we can use that for compression. So more accurately, if we do a delta between the token I and token I minus one's KV cache, we will see that distribution is much closer to 0 compared to original distribution, which means that it can be more easily compressed. And the second opportunity is that the quantization, like different layers have different quantization sensitivities. So basically, for the very first few layers, we cannot quantize them too aggressively. But for the later layers, we can aggressively quantize them without hurting the accuracy. By accuracy, I mean the inference, by accuracy is like actually the ChatGPT graded accuracy. So it's like ChatGPT counted as accurate is accurate. And yeah, so here we can see that the first 3 layers are like after the same level of quantization, the first 3 layers drop the accuracy by about 50%. But for the 20 to 23 layer, it only dropped down the accuracy by only like 2 to 3%. So we can do like much aggressive quantization to later layers, but a more mild quantizations to earlier layers for better compression. And the third opportunity is to do arithmetic encoding. Basically, it is because that if you represent it into a simple, like into traditional floating point representation, it's not enough because it's not efficient because the amount of bytes required to represent each number is fixed. And if we do variable lengthing, if we can represent each number with variable bit length, we can achieve a better compression. So there's existing technique called arithmetic encoding to do that. Okay, and we did a quick set of evaluation. I will skip should I skip? No. Yeah. Okay, so basically, we mainly do we will show the evaluation on Longchat on Llama 70B, but we also have a lot of other experiments to show the trade-off is better. So here in this figure, with the workload is that we're using Longchat and model is Llama 70B, and the link to load KV cache is about 3 gigabits per second, and that's a relatively on the low end of the data center. So here, the FP8 quantization is here highlighted in a blue circle, and the other one is FP16 and FP6. So we can see that the accuracy versus size of KV cache trade-off, our green curve here is much better. And in terms of time to first token, the improvement is also obvious. It's about 2x improvement. Yeah. Oh, I forgot to click. Yeah. And this concludes our first work. And the second work is to flexible join multiple KV caches. So here, the left engine is the vLLM engine with the KV cache blending feature, and the right one will be standard vLLM engine. And our workload is that we will have 5 retrieved chunks from the document, and the total context length will be like 25,000 tokens. And let's type some queries here. So example query maybe. So this is still about FFmpeg, so I'll still use FFmpeg as example. Tell me something about FFmpeg in 10 words. And copy paste here. So let's start from the standard vLLM and start from the LLM cache powered vLLM. We can see the response delay here with our KV cache blending feature. The response delay is about 1.73 seconds. And here the response delay is about 5.41 seconds. We can see that the output is slightly changing. Yeah, this optimization will change the output, but it still has a very similar semantic meaning and it does not hurt accuracy. So the reason of us introducing this technique is that because the KV cache of a chunk cannot be reused if it follows after some new text. And that's why there's prefix caching instead of like caching any data in vLLM. So for example, if the document 1 is a short FIFA news and the document 2 is a more up-to-date FIFA news, and we ask the question, who scored the most goals at FIFA World Cups, Messi or Ronaldo? If we do the text, concatenate them together, we'll get the right answer. But if we concatenate KV cache together, we'll get a wrong answer. So that's why we need the reason of that phenomena is because if we use text as the input and do query, we can do cross attention between them. We can calculate their relationship between each other. But if we simply concatenate the KV cache between them, there will be no cross attention between them. And then we need to recover those part of cross attention for a more accurate result. So there's a rough trade-off between different approaches. If we do full prefill without KV caching, it will be slow, but much higher quality. But if we directly reuse the KV cache, the answer quality will greatly drop. And what we want to do is that we will have a low inference time while still have a high answer quality. And our intuition is that we only need to selectively prefill a few tokens. So basically, we are still doing the prefill, but while doing the prefill, we will check which tokens are changing and which tokens are not. Sorry, the KV cache of which tokens is changing and the KV cache of which tokens are not changing. And we found that only a small subset of the tokens changes KV cache, and we can use it. We can leverage that property to save the computation. So here is an illustrative figure. So full prefill, it will prefill all the layers, but our selective prefill will only prefill a part of the tokens based on so the first layer will still do a full prefill, but then we found that maybe some of the tokens is changing a lot, but some of the tokens are not. And we only prefill on those with those highly changed tokens, and we will not do prefill on those not changed tokens. Yeah, and here we have a representative result where compared to the full prefill and no prefill, our selective prefill strategy has higher F1 score and lower time to first token, and it can be even sometimes better than the full prefill. And the dataset here is a Samsung dataset, which is a daily use of phone, and the model is Llama 7DB and on two A40 GPUs. Okay, and you can try it yourself on those demos. So here, basically, we found that in terms of the trade-off for cost and delay, all other approaches are on a trade-off which is much altering this trade-off. But what we want to do is that we want to have a very efficient knowledge sharing, which can reduce the cost and the delay simultaneously. And that's LLM cache with vLLM, of course. And thank you. Are there any questions from the audience?
Yeah, no, I think we're great. Thanks a lot. I have a few questions myself, but there's some questions that were asked ahead of time. Yeah, one from Kunjan. For disaggregated serving, kind of related to the Nickel thing, have you compared Nickel inner host to inner process using the CUDA IPC interface for full decode? Yeah, I mean, it sounds like you've just used Nickel, but are you, I guess?
Yeah, I'm just using Nickel, so I'm not comparing them. But from what I heard from industry folks, as long as the connection is accelerated, by accelerated I mean RDMA or even more up-to-date link techniques, the transmission delay won't be dominant. So as long as you have a decent connection, is always enough. As long as the engineering is doing carefully. Yeah.
Yeah.
Are there any other questions from the audience from the chat? Let me see.
There's another question on, have you considered utilizing CPU memory or GPU direct RDMA when using an SSD? I think the latter is maybe for like consumer GPUs, but
yes.
Yeah.
So yeah, so in the current view of vLLM, disk is not included in the storage tier for now, and that's why I'm not supporting that for now. But inside our own cache, we do have plans to add like more up-to-date storage techniques like GPU direct storage, and integrate it into vLLM cache for faster storage. So the short answer is that for our vLLM is the storage part on disk is not there yet, but for our cache we're optimizing for it. And yeah. Sorry. Yeah, is there any other questions from the audience? Optical interconnection for KV cache transfer.
I mean, yeah, any faster interconnect will help, right?
So basically because like nowadays in models, like in a lot of models, they're trying to compress the KV cache smaller and smaller. So the current state is that as long as you have like RDMA in your data center, and if you do pipeline transfer across layers well, the KV cache transfer delay is no longer dominant. It's mainly dominated by model forwarding.
Yeah.
I just have a question. In terms of disaggregated prefill, like I see that it's only optimal for certain configuration of sequence length, input and output. And so we expect that chunk prefill might still be applicable for certain configurations. So we expect that it'll be some sort of a intelligent layer that sort of routes them based on this, like they can coexist.
Sorry, can you say that again?
Is there a scenario where we can use both chunk prefill in certain vLLM instances and disaggregated prefill on certain other
Yes.
instances?
Yes, they can coexist.
Okay.
And I was also expecting that. So basically, because there will be long context in the future, and chunk prefill is a good way to limit the peak memory usage. So we do want to support disaggregated prefill and chunk prefill together. And I see some questions from the audience. Let me see. Okay, so here is a question from Chen Di. So for KV cache, how does selective prefill pick change the prefill token using hash or something else? No. So basically, we are picking those tokens by doing a full prefill on the first layer and compare the KV cache to the already cached one and calculate the difference between them and do a thresholding there to pick the what tokens we want to do, but we want to do selective prefill there. Yeah, hopefully that answers your question. And I also see Chen Di posted another question where resume my previous question for disaggregated prefilling. Would it patch different input length to different batch or purely based on arrival time? Again, that depends on the scheduler. So basically, vLLM itself does not natively support separating different jobs based on the input length to different queues. That's not natively supported. So basically, the current practice is to do it by the scheduler on top of vLLM to schedule the requests on different machines. For example, short requests to those machines that only serves for short requests, and long requests for those machines that mainly serves for long request. Yeah. So another question from Dirk. So I understand that there is ongoing work, right? Has anything already been merged into VM? What's the current status? So basically, the current status is that we are mainly handling so the implementation difficulty comes from the distributed communication part. The reason is that for torch.distributed technical stack, there needs to be a global barrier when initializing any distributed connection groups. For example, if we have 10 processes and we only want to build a group for process 1, 2, 3, then all processes from 1 to 10 needs to barrier. Even for those processes that is outside the group, it needs to barrier as well. And that kind of difficulty is hugely complicating the code. And CacheGen provides an alternative for us to simplify it. And I'm editing my PR according to it. Yeah. So basically, we do want to make the first implementation as clean as possible because it will be much harder to change it in the future. Yeah. And there's a question from Maxim. You mentioned that during doc1 plus doc2 process, you select which part of KV cache use. Could you explain how do you understand it? So basically, we are selecting those tokens that their cached KV cache is different from what we computed KV cache on the first layer. So we will do a delta there, and we will do a delta between the actually computed KV cache on the first layer versus the cached KV cache on the disk. And the difference we'll pick those tokens based on the difference. Okay, another question from Victor. If the current maximum GPU memory and CPU memory and GPU memory all triples in size, oh, interesting. Will vLLM be able to take advantage of the larger CPU GPU memory? What if 100 plus times larger? So the short answer is probably no. The main reason is that though vLLM can use those extra memories, but it comes at the cost of Python implementation. And Python implementation has a very poor scalability, especially when the object we're handling, like CPU, GPU memory, becomes much larger.
Yeah, definitely if the memory bandwidth scales like a large amount.
Yeah. And and in the V1 we are trying our best to make sure the overhead is ON, but it's still ON, it's not O1. So yeah. Is your graph like from Kunjan? Is your graph saying that KV cache on S3 is faster than on CPU on SSD? No, of course, much faster on CPU and SSD. And on S3, we really need the compression to make sure the loading provides benefit. But on CPU and SSD, even if we just save the uncompressed KV cache, the loading time will still be smaller than the prefill time. So it still provides benefit. But of course, with compression, it can be much faster. Okay. From Jinkia, and slightly unrelated, is there any plan to make APC a default once more on the Optimus like these are merged in? Recall seeing some diminishing benefits when increasing concurrent requests in vLLM docs. So that's why we need to have a V1. Yeah. So there will be vLLM V1 rolling out soon, and it has a much more efficient prefix caching, and it's prefix caching centric. So everything is around that. And at there, we will have a much better architecture to support this APC as a default feature.
Yeah, and that's also where, to answer a previous question, where we'll be working on supporting prefix caching for multimodal, particularly like vision language models, and thinking through this now.
I get
thanks.
the answer to the larger memory thing. Is that because of the PyTorch limitation, or is it hardware limitation?
Mainly Python limitation. So because vLLM is written in Python, Python is slow. And the scalability of is handling a very, very large amount of objects. So basically, vLLM handle those GPU memory and CPU memory in terms of blocks. And to manipulate, if you have 100x more CPU or GPU memory, you have 100x more blocks. And to handle 100x more blocks you cannot do it in the handling time for that by purely just shuffling them. It will be ON, and it will be much slower when the number of those blocks becomes much larger.
So it doesn't matter how much is the bandwidth. No matter how fast or how larger the hardware is, the Python won't be able to take advantage of that larger, faster hardware.
Well, it depends on like what are you talking about, like prefix caching and like matching in those things versus like the model forward pass or like supporting larger contexts, like it depends on sort of like what work do we need to do in Python and like what work.
I would say both. Yeah, just wherever it can take advantage of the faster, larger memory hardware.
So I guess almost every part except for the scheduler. Yeah. So scheduler has a scheduling overhead, and after it's scheduling, it will run the model on the GPU, and it will do the memory movement between CPU and GPU. Except for the scheduling overhead, every other part can benefit from a larger pool of GPU or CPU memory, I guess. By having more KV cache cached in GPU and CPU. Yeah.
Okay. Yeah. Thanks.
Yeah, but for the current status, at the current size of the GPU CPU memory, the Python's overhead is still okay at the current size of GPU CPU memory. And I heard that the GPU memory won't increase significantly in recent years because the high bandwidth GPU memory manufacturer has limited capacity each year.
But there are tiered memory design coming that's going to make it bigger.
Yeah,
I guess
that's going to make it bigger. Yes.
If it does happen, I guess because so you just have more parallel built into it, right? Because each I was imagine that as a scheduler is per node limit, or is that overall job limit?
Sorry, can you say that again?
Yeah, the scheduler is for like a single instance of vLLM, right? So you can like scale that out horizontally in terms of having like more vLLM runners on more nodes or more GPUs. And these obviously aren't going to affect each other, but it seemed like you were talking more about individual accelerators or individual systems like scaling up.
Yeah. So if you have more scheduler, that problem should be resolved.
Yes, yeah. But you also talked about like hierarchical memory, which is like, you know, we're talking more about like the memory bandwidth like of the GPU itself. Like, right, if this doesn't keep scaling, like if that keeps scaling, then that's harder to keep up with. But like if there's just like more memory at the same bandwidth, this is like less scaling. I mean, like of course, like scaling, there's going to be bottlenecks. It's yeah.
Thanks.
A bit of a hard thing.
Yeah. So like we will process to other questions. There's still a lot. So like I don't want to finish them before the
have a roadmap for like these multi-GPU deployments? Because this is like a really interesting idea. It's a really clever way to use the hardware. But how does it tie in with other strategies like pipeline parallelism or I know there's a data parallelism PR out there as well. Is there like a roadmap or someone who's kind of trying to take a high level of?
Yeah, it will be in the next year's roadmap. Yeah, next
year's roadmap. Okay.
Yeah, next year's roadmap.
Where are those discussions happening? Is that like on Slack or is that kind of? I'd like to get a bit
mainly on Slack.
Okay. All right.
Yeah.
Thank you.
But also like RFCs in the issues. If you want to look for some of them, like we have sort of, you know, pinned issue. Like there's a pinned issue for the vLLM roadmap for this quarter. Usually we do them on like a quarterly basis. And then there's also a pinned one for the V1 engine architecture. So yeah, check out the issues page on vLLM.
All right, thanks.
And question from, sorry, are we running out of time or?
No, yeah. I guess like if we could just go through like the slides to like end, but then we can still stay on and answer more questions. I think that would be good.
Sure. So from Sanjay Lee, for the desired prefill to implement, does your implementation exploit temporal buffers or copy directly into the KV blocks? So yeah, it's using the temporal buffers. The reason is that we do not want to put the KV cache right into the GPU until the request is actually being executed. We want to delay the movement of KV cache until it's actually being executed. So that's why we will have a temporal buffer there. Also, I'm curious whether it supports asynchronous send receive to reduce communication latency. Yes. We are supporting async send and receive. Oh, sorry. So basically our send will be asynchronous, but our receive will be synchronous. Because if you start the receive, then typically it indicates that this request is already being processed. So we want to make sure the data is ready before we actually execute the computation. And from Oral, were you doing any voice or image LLMs, where TTFT will be even more sensitive? Yeah, we are actually working on that. And from Sanjeev, please describe again what was the logic for deciding whether to reuse the previous knowledge context for a new query or need to rebuild a new knowledge context. Okay. So basically, in our implementation, we are chunking the input, and we'll reuse a chunk if the chunk matches the input text. That's what we're doing for now. And chunking, our chunk size will be 256. Okay, from Sar, combining APC with disaggregated prefill decode is challenging since potentially two instances create KV cache. Is that right statement? Yes, and that's why. So basically, doing APC trivially is easy. By trivially, I mean that we always do a transfer regardless of the KV cache hit. But if we want to avoid KV cache transfer when the decode instance has KV cache hit, then it will become much trickier to do that. So I will say that the implementation, if we want to reduce the total amount of transfer, we need careful implementation. But if we are mainly caring about the SLO, then it should be fine.
Yeah, this kind of goes towards the structure of the system, I guess, where you like if the KV cache is transferred between a prefill and a decode worker with like a router or a storage in between versus prefill workers communicating directly to decode workers. Depending on the architecture, this becomes like, easier or completely infeasible, I guess.
Yeah. Is there any other questions from the audience?
No, yeah, I think we're right over perfectly. Yeah. So if you could click to the next slide. Or
there's
the
next slide. Okay.
Yeah, the next one. I guess this is kind of the discussion one. Yeah, so thanks everyone for visiting and the attending and having the good discussion. Of course, we're contributors to vLLM ourselves. We'd love if you want to contribute as well, or if you're a heavy user. There's many ways to get started, but a good thing, as we mentioned before, is to check out some of the RFCs or ongoing projects and just commenting or posting in there to get the attention of people working on that. And of course, look for good first issues if you're looking to start your contributions. As always, give us feedback on office hours, or if you're interested in giving a talk or covering a special topic. There was just a meetup yesterday at Snowflake for vLLM, and so for other upcoming events, we'll be at NeurIPS in December. So definitely drop by and say hi if you're there. And yeah, we're hiring at Neural Magic. If you want to join and work on vLLM, we're always looking for more people. So yeah, and with that, that's pretty much it. Kuntai, thanks a lot for your presentation.
Thank you, Kuntai.
Yeah, thanks, Michael, for your invitation. Thanks for everyone who is coming.
Yeah, and that'll be all. Thanks a lot.